Welcome to The Explainer. Today, we're diving deep into something that makes your entire digital life possible, but that you never ever see: memory management. Seriously, have you ever just looked at your screen with all the browser tabs, Spotify, a game, and your chat apps all running at once, and just wondered, how? How is all of that stuff crammed into the physical memory chips inside this machine without the whole thing just grinding to a halt?
Well, the answer is kind of wild. It turns out, to make it all work, your computer's operating system is playing this non-stop, high-stakes game of Tetris with your data. It's constantly shuffling and fitting every little piece into a finite space. So let's break down how that game is played.
Okay, so first things first, why is this even a problem? It all starts with a fundamental rule of how computers work that puts everything under pressure. And this is the rule that causes all the trouble. It's a design called the von Neumann architecture, and it basically says that for any program to actually run, to do anything at all, it has to be loaded from your slow hard drive into your super fast main memory, your RAM. That's the computer's main workspace. So here's the bottom line. We all live in a multitasking world. We want to run a dozen things at once. But every single one of those programs has to fight for a spot in a very limited, very physical amount of RAM. This creates a constant tug of war for resources. With all these programs basically yelling, "Pick me," the operating system needs some smart strategies to figure out, where to put them all. The first really big idea here is called relocation. See, in the old days, a program might have been built to only run at a specific memory address. Let's say address 1000. If something else was already parked in that spot, too bad, you're out of luck. Relocation gives the OS the flexibility to say, hey, address 1000 is taken, but I see a nice open spot over at 5000. Let's just put you there instead. It's a game changer. Now, that flexibility is awesome, but it brings up a new problem, right? If you have a bunch of open spots or holes in memory, which one do you pick? Believe it or not, this decision can make a huge difference in performance. And this leads to a few different game plans. You've got First Fit, which is all about speed. It just grabs the very first space it finds that's big enough. Then there's Best Fit, which is pickier. It scans all the options to find the tightest possible spot to avoid wasting space. But that scanning takes more time. It's that classic trade-off. Do you want to be fast or do you want to be tidy? But here's the catch. As you load programs and then close them, you leave behind all these little unused gaps. This is called fragmentation. It's a huge pain because you might have, say, 2 gigabytes of total free memory, but if it's chopped up into thousands of tiny little slivers, you can't even load a 100 megabyte program. So how do you fight back against all that mess? Well, one really clever solution is called the buddy system. The basic idea is to only deal with memory chunks that are powers of 2, like 64K, 128K, 256K. If you need space, you take a big block and just keep splitting it in half until you get a piece that's just right. And here's the real magic. Because they were split perfectly in half, when a program is done, these buddy blocks can merge back together perfectly, keeping memory neat and clean. Okay, so these are all smart ways to manage the physical chaos. But at the end of the day, we're still just playing Tetris in a pretty small box. But what if we could change the game completely? What if the operating system could just lie? What if it could create an illusion of a massive, clean, perfectly organized memory space for every single app, all at the same time? This is the solution. It's an absolutely brilliant concept called virtual memory, and it is truly one of the most important ideas in all of modern computing. The OS literally fools each program into thinking it has the whole computer to itself with this gigantic, pristine, wide-open memory space. The program has no clue about the messy, fragmented reality of the physical RAM chips underneath. So how on earth does the OS pull off this incredible magic trick? It uses a technique called paging. And honestly, the best way to wrap your head around it is to think about reading a book. Okay, check this out. Your entire program, let's say it's a video game, is like a huge book sitting on your bookshelf. That bookshelf is your computer's storage disk. Now, you don't need the whole book on your desk just to read chapter 3, right? You just grab the couple of pages you're actually reading. Paging is the exact same idea. The OS breaks the program into fixed-size pages and only loads the ones it needs right now into the physical RAM, which is your desk. Of course, an illusion is only good if you can keep it going. So, what happens when the program needs a page that isn't on the desk? That's when something called a page fault happens. Now, it sounds like an error, but it's not. It's actually a totally normal part of how this all works. It's basically the program raising its hand and saying, "Hey OS, I need that page from the bookshelf." The OS then just pauses the program for a split second, finds the page it needs on the disk, and brings it into an open spot in RAM. But what happens when there are no open spots in RAM? Well, then the OS has to decide which page to kick out to make room. And, you guessed it, it needs a policy for that too. A simple one is FIFO, or first in, first out. Just get rid of the oldest page. A smarter one is LRU, least recently used, which says, let's replace the page that nobody's touched in the longest time. And then you have others like NFU, not frequently used, which keeps account and kicks out the one with the lowest score. And picking the right policy is absolutely critical for performance. I mean, look at this. This chart shows us just how big a deal it is. If you only find the page you need in RAM half the time, a 50% hit rate, your average access time is, let's say, 125 units. But if you use a smarter policy and get that hit rate up to 80%, your access time plummets down to 18 units. Fewer trips to the bookshelf mean a way, way faster computer. Now, the absolute worst case scenario here is a condition called thrashing. This is when the system has so many page faults that the computer spends almost all its time just swapping pages back and forth from the disk. It's like a reader who spends more time running to the bookshelf and back than actually reading the book. The computer gets incredibly slow because it's completely bogged down just trying to manage its own memory. So when you really put it all together, it boils down to this. Your computer is constantly playing a high-stakes game of Tetris with data, and it uses a brilliant illusion to make the game board seem infinitely large. From managing the real physical squeeze to creating this incredible virtual world, it's a complex balancing act that makes our modern multitasking lives possible. So what's the big takeaway from all this? It's that so much of what makes our computers feel fast and limitless is actually a system of incredibly clever tricks and illusions, all designed to hide the very real physical limits of our hardware. So the next time you're switching between dozens of apps and it all feels instant, just take a second to appreciate that invisible game of Tetris and the beautiful illusion of infinite space that's happening thousands of times every second just for you.